I need to,
It's got an update on it.
I need to be able to see what I'm doing. Okay.
Okay. So let me introduce John Hebberger. He's the Vice President of Geologists at Jackson Hole in charge of our program, something that he does exceedingly well. And in fact, if you're interested in giving a talk, 2019 is pretty much all booked.
Not completely.
Why? There's 3 openings on it. Hey, Bill, just grab some chairs off the wall. And it's all because of John and the contacts that he's managed to put together with all the different schools and universities around us. So he does a masterful job of this. And I also have to tell you that John didn't actually sign up for this. We were going to have a gentleman from Scotland, our leader of the field trip over to Scotland in 2015, I think it was. Unfortunately, he could not make it due to some health issues. And lo and behold, John, and then tomorrow with Mike Adler at the Senior Center, immediately jumped into the fray and are giving talks tonight and tomorrow. I do need to mention about Mike. Mike's talk is a continuation of what he was talking about last time here, 2 weeks ago Tuesday, about Jupiter and Saturn, except he's going to get into a lot of the little stuff, the rovers on Mars, the latest sort of probes that have gotten onto satellites and comets, and it should be a very interesting, and knowing Michael, a very well photographed presentation of the planets and other debris around us. Now, back to John. John went to University of Missouri, Columbia, got his degrees there in geology, was immediately sucked away by Chevron and had a career with them for roughly 30 years. He had, unlike me, who got to stay home all the time and just traveled to all the garden spots in the world, John actually got to go to some of the garden spots of the world. And if you ever want an interesting discussion, talk to him about the life in Papua New Guinea. An interesting assignment. But John is a real, in my mind, cornerstone not only to the geologists at Jackson Hole, but to the Library Foundation, to all kinds of other things. You can never get him in March because he's doing taxes for minority people. And that's probably not properly said, but anyway, he really does a lot of wonderful things for us. Probably the most of which is this presentation of the programs that he puts on here. So, without further ado, let's welcome our speaker, John Hebberger.
Yeah, John, if you'll get those lights.
Oh, one last thing. We shoot people that phones ring.
Yep.
Get it out and turn it off.
Yeah. All right, good evening, everybody, and thanks for coming. Everybody is probably here because of this place we live in. It's probably not an accident. This is probably one of the most self-selected communities in North America, would be my guess. I have regularly, when our visitors come and talk to us, give presentations from various universities, organizations, I typically ask them if they know of another place on Earth about this size aerially where you can see the evidence of as many geologic events that have helped shape that landscape as here, anywhere else on Earth. And to this point, Mr. Surdam, I'll throw that challenge out to you too. Nobody has been able to come up with another place on Earth that actually you can see more geologic events, evidence of it, than you can right here. And what I hope to leave you with by the time this talk is completed is the understanding of what that, at least an outline of what those events are, and some real appreciation, a greater appreciation when you look around this area at where we live. So it's an amazing place, and it's an amazing place because of the geology, and that's the real story that I want to leave you with here tonight. So, there are a number of things I hope to accomplish, give you a sense of how much time is involved in some of the things that you can see. I certainly want you to be able to look at things and have a greater appreciation for what you're seeing and why it's there. And certainly, again, I really do want to leave you with a sense of how important the geology is to everything that's here, including us, why we're here. So hopefully that will be pretty clear by the time I'm done. If not, shoot me. So this is a long story. I'm not going to spend billions of years talking about it, but it is a multi-billion year story, literally, very nearly 3 billion years of time that we're talking about. The most significant things that we see, probably though, are primarily within recent geologic time, only about, say, the last 70, 65 million years, something like that. And there are a couple of events that are really important. One is a major compressional event that formed most of the mountain ranges and the basins across the state of Wyoming, all the way to the Black Hills. Of course, Yellowstone, one of the world's great volcanoes. An ongoing extensional event, the Basin and Range event, that stretches from here all the way to the Sierra Nevadas. That is the reason that this valley is here and the reason the Teton Range is here. And then glaciation, which not as big of an event from a geologic perspective, but very important in terms of sculpting the landscape that we live in here. So, and a lot of the stuff is ongoing right now. From a geologist's perspective, glaciation is arguably, maybe still ongoing. So let's move on then, and this is a real quick look at the geologic timescale. We're not going to dive into the details of this. Here's Earth history from 4.6 billion years of it, and most of what we are interested in primarily is the last 540 or so million years. There are some things that go back to almost 3 billion years in the past. Another one at about 765 million years ago, and there's a 2 billion year gap in there that I will try and give you some sense of what's happened, because we don't see any evidence for what happened in this local area during that time. And so let's move on then, and these are the major features that and that we want to talk about. We've got the Snake River Plain up here, which is the track of the Yellowstone hotspot, Yellowstone itself, the Ipsarika Mountains, of course, Jackson Hole and the Teton Range, the Gros Ventre Mountains, which not long ago stretched all the way over into Idaho, the Fold and Thrust Belt, which extends from Mexico all the way up to northern Canada, and then these normal faults that we see here, including the Teton Fault here. So those are all things that we want to talk about, and that I want to give you some sense of what they are, why they're here. So if we step really back and look from space, if you will, though this isn't really a space image, but that's what it looks like. The things that I really want to talk about, at least initially here, are these compressional events from the Black Hills out here, the Wind River Range all the way down Front Range in Colorado. We will talk about that. We will talk about this yellow outline here, which is the boundary of the Basin and Range event that is ongoing today. And you should be able to see that the Teton Range, Jackson Hole, is within the boundary of that Basin and Range extensional event. You can see where Yellowstone began about 17 million years ago, 16.5 million years ago out here. The Snake River Plain is the result of the migration of that feature into the continent to where it is today, just 60, 100 miles north of us here. So those are the things that we want to talk about, want to explain here during this presentation, the primary ones. So we can see evidence right here of these very large regional continental scale events, most of them. So what I really want to do then is to walk through time with you. I want to go back in time nearly 3 billion years ago and walk forward to today and give you a sense of how this place that we live in has developed, why it is so wonderful, why it's such a spectacular place. And we're going to start billions of years ago, very nearly 3 billion years ago, and look at the core of the Teton Range. And those rocks that you see in the core of the Teton Range are between 2.6, 2.8 billion years in age. And it is, to a very large extent, the reason that they are so jagged and so spectacular is a result of two things. One is the type of rock. The crystalline rock, think of it as granite, if you will. It's more complex than that, but think of it as granites. The reason that it is so jagged, these peaks, is partly because they are so resistant to erosion. And the other factor is that is such a very young mountain range, probably 4 million years in age. And then the last thing that I want to mention is that there is evidence for a zone of Himalayan style suture. In other words, think of India smashing into the southern belly of Asia today. There is evidence in the Teton Range that is being documented of the earliest known event like that occurring on Earth, and the evidence for that exists in the Teton Range here. So that's fairly new work in the last decade, and we had Ron Frost out here a couple of years ago, and he's going to be out next spring to actually talk specifically about that. So those rocks, those 2.6, 2.8 billion year old rocks are gneisses. Think of granites as, as a nice sort of generic term for it. It's crystalline rocks, either injected deep into the earth or metamorphosed. And you can also see, though, evidence for, this would be India, this would be Asia. There is evidence, again, for a similar event like this having occurred nearly 2.6 billion years ago, and that evidence exists in the Teton Range. And that's as far back as anybody on Earth has been able to see evidence for that kind of event happening. So, all right, there's a 2 billion year gap to the next thing that we see here in the Jackson Hole area. What is that? And this is a brief way to try and explain some of that. So Wyoming is that white block there, right here. This is the Wyoming Province. All the pink rocks are greater than 2.5 billion years in age. All the other colored rocks are younger. So what you're looking at is basically the assembly of North America, the North American craton or plate, through time from 2.5 or so billion years ago. All these other colors, for instance, in here like this, you're seeing this old block smash into this block and become accreted to it, stick together, if you will, and you're seeing that seam in there with those younger rocks. And then you can see the age here of 1.8, 1.6, the Grenville 1.4, 1.0. You're seeing the assembly of North America through time. So we don't see direct evidence of that here, but if we step back just a little ways outside of Wyoming, we see that there's a whole lot going on around this province, if you will. We just don't see direct evidence of it here. So it's not like nothing is happening. There's a lot happening. We just don't see the direct evidence of it here in Jackson Hole. So there's my explanation of 2 billion years of Earth history, all in one slide. So the next thing we see is about 765 million years ago. The next thing we see is evidence for one of the supercontinents that has existed on Earth. Many of you may have heard of Pangea, which is the most recent one that existed. It began to break up about 250 million years ago, 250 million years ago. This one began to break up. It's the one that preceded Pangea, and it's the one that began to break up around 750 million years ago, roughly, give or take, some millions of years. And what we see is that Laurentia is the geologic term for North America, if you will. And if you look in here, here's the equator. That is Hudson Bay. There are the Great Lakes. So and the blue block is Wyoming. North America, Laurentia, if you will, is on its side and essentially at the equator, 750 million years ago. And what is happening is this supercontinent is breaking apart at that point in time. So what do we see? We see basically something like, think of the Red Sea opening up in the middle of this, what was a supercontinent. And that's what this symboling, this is supposed to indicate. What you see is that south part of China was right to the west of us today. In other words, a big piece of China was not far away. A piece of Siberia wasn't that far away. Australia wasn't, pieces of it weren't that far away. This is the best guess as to what the Earth looked like, 3/4 of a billion years ago. A very, very different place in a lot of ways. And so Wyoming, the Wyoming Province, is at the edge of that craton that is forming as a result of the breakup of this supercontinent 3/4 of a billion years ago. And we can see evidence for that in Mount Moraine and a lot of other places in the Teton Range. The Black Dike, Mount Morane's famous Black Dike, is evidence of that breakup. What we're seeing is a situation like here where the supercontinent is being broken apart, pulled apart, the crust is thinning. Volcanism comes up as a result of that, and if you're aware of the Red Sea, there are volcanoes around the perimeter of the Red Sea. So what we're seeing here, when you look at the Black Dike and the other dike in the Teton Range, is you're actually seeing that subterranean plumbing system of this ancient volcanic system that is a result of the breakup of that supercontinent 3/4 of a billion years ago. So think about that when you look at at Mount Moraine next time. We come forward a mere 200 some odd million years, and we see evidence for the next thing that we can see here, and that is that really continent-wide there's a continent-wide erosional event occurring across most of what we think of as North America today. And that happened right at the beginning of the Cambrian. So when life, as we talk about the Cambrian Explosion, that's when that is occurring. Life explodes on Earth. And what you see here in the sandstone cap on the top of Mount Moraine is that sandstone is sitting on top of the dike that is 756 million years old, and on top of these even much, much older, of course, crystalline rocks. So you're seeing evidence for continent-wide, basically, erosion and then deposition that sweeps across North America at that point, beginning in the Cambrian time. So then we get into more familiar territory, at least for some of us, and that's Paleozoic. So we're talking about 540, 250 million years ago. Wyoming, here's the state boundaries. And what is happening is that the sea is coming, the sea is going, back and forth. It's sweeping across basically a very near sea level. The continent, most of the continent is very near sea level. So the sea comes, the sea goes. We're near the equator. And so what you end up having is a lot of carbonate rocks. Think of the Bahamas. Think of South Florida. You have carbonate rocks, limestones, and dolomites being deposited. Lots of fossils in the rocks, as you can see here. But look at this. When you look at the mountains here and see these rocks, you see a continuous sequence of rocks. But what I want you to recognize is that there are vast gaps in the time there. So it's like a book where you've taken out over half the pages. They just aren't there. So there is no record for these big gaps in time here. There's either no deposition going on and/or there's erosion occurring. So there are no rocks that represent those periods in time. So it looks like when you look at the cliffs here, say where the tram goes up, and you look at those big carbonate cliffs, it looks like a continuous sequence of rocks, and it is, but there are vast gaps in time in those rocks, represented by layers in those rocks. So as we come forward in time, and so now we're only 250 to 145 million years ago in the Triassic, Jurassic. North America is moving further north away from the equator. It's still very low relief, relatively speaking, certainly in this part of the continent. You have shallow oceans that at times come sweeping across. You have vast sand dunes, think of the Sahara, if you will, that are seen in rocks, evidence of environments like that in some of the rocks. It's an age of reptiles. We're at the very beginning of when dinosaurs become really significant. But you can see evidence. This is from in Teton County. This is a place where you can actually see theropod dinosaur tracks on a boulder in Teton County. And a lot of these rocks are red. So when you look at red rocks across Wyoming, especially the red sandstones, you're looking at these rocks from this period of time. So as we come further then, forward in time, so here we are, North America is still pretty darn flat, near sea level. It's turned upright the way we think of it today. It's moved further from the equator. And Wyoming is right here. And what you see here is there was a shallow epicontinental sea, a shallow sea that stretched from the Canadian Arctic all the way to the opening Gulf of Mexico. So when we say shallow, we're still talking maybe 1,000 feet deep or something, but we're not talking about 10,000 or 15,000 or 20,000 feet of water depth. And you can see that Wyoming is on the western edge of that seaway. So the rock section here is pretty continuous. There's a gap in time here, but it's a pretty continuous record of what happens during the Cretaceous. And this is the age of dinosaurs. And the blue represent marine rocks formed in the ocean, and the yellow rocks represent rocks formed on the shore. This is a neat figure here. So time in this direction, younger up here. Think of Jackson Hole right here, and this says 200 miles west, this says 200 miles east. What you're looking at then is a record through time of where that seashore is with respect to the town of Jackson, of course, which doesn't exist for many millions of years yet, but what you can see is that the shore of that sea was to the east of Jackson, then it swept to the west, so we're underwater. It comes back, it sweeps back to the east, and we're above sea level. It comes back, the ocean comes back in, we're underwater again. It goes away then, and the ocean has never come back. Maybe 50, 100 million years from now, I don't know, I'm not going to predict. But there's a very clear record of this interior seaway in Wyoming. And it's also the reason that Wyoming is probably the most important producer of coal. It has the greatest resources of coal, arguably anywhere in the world. It's because of the environment that was along this seashore, during the Cretaceous. So that's where most of Wyoming's money comes from, so it's important to you and me, even though it's declining. So for nearly 500 million years then that we have a good geologic record, we can see that Wyoming is basically at sea level, slightly above, slightly below, right at. And during this time, there are periods when there is no deposition, but there's also a lot of rocks that are being deposited, thousands of feet of rocks that we see today near the sea, in the sea, just on board. And these rocks, as rocks were deposited as flat layers. So for hundreds of millions of years, Wyoming, in a lot of ways, was a pretty dull place, unless you want to watch the oceans come and the oceans go over millions of years and see rocks being deposited. Those rocks, much of them across the state of Wyoming, are no longer flat. In some cases, they're vertical to even overturned, and that's what we're going to begin to talk about here now. Because roughly, 65 million years ago, we could say 60, we could say 75. It depends on exactly, how you want to talk about things. Some really major events began to occur in this part of the world that we see evidence of, and it's a result of these events that caused Wyoming to be what the reason that people come here. They come to see the mountains. They're not so worried about the basins in between. But both of those, the very deep, vast basins and the high mountain ranges, with the exception of the Basaricas and the exception of the Teton Range, were all formed as a result of this compressional event that we're going to talk about, we're going to see evidence of right now. And then we'll talk about Yellowstone, the supervolcano, if you will, the major volcano near us. So this is, a picture, a cartoon, if you will, of what is happening 65, 75 million years ago. And it is a collision. North America is moving west. The Pacific Ocean, this ancestral Pacific Ocean, is moving east. There's a subduction zone, like this diagram right here. There's compression, that's the key thing. And so there are volcanoes along the coast and there are mountains that form inboard all the way across Wyoming. And so this compressional event is really what you see evidence of when you drive east from here all the way to the Black Hills. All those mountain ranges are a result. You leave the Tetons behind, it's not, and not the Apsaricas. Everything else that you see is a result of this compressional event. So if we go back, about that time or just slightly before, what you see is this vast, it was even a bigger Pacific Ocean, this ancestral Pacific Ocean out here. And these red lines are the spreading centers. It's like the mid-Atlantic ridge today. It's where oceanic crust is being created. And what you see is that crust is moving away from those spreading centers in the direction of those white arrows. And what you see is that North America is moving basically west. And what that results in is the continents are thicker, lighter than the oceanic crust. And almost invariably, the continents override the oceanic crust and it subducts. It disappears down underneath the continents. And that's what these red lines and the teeth here are to indicate, is that was subduction going on. And that's why you have this compressional event that forms the mountain ranges and the basins across Wyoming. So here's one example of the result of that. So the town of Jackson is right here. Here's the Tetons, which weren't there yet, and Jackson Hole, which wasn't here yet. You see the Grovant Mountains, which extended over into Idaho. We see the thrust belt here. And if you look at this pink line, that's this cross-section right here. And what you see as a result of that compression, you have slices, if you will, of the sedimentary rocks being shoved on top of each other, folded. So you can see that blue layer is the same layer of rock on top of the same layer on top of the same layer. It's very complex geology, but that's what we see when we look to the west of us here and look at what you know as the Snake River Range or know as the Wyoming Range to the south of us. That is the thrust belt. And this is the kind of geology that you see in it here. To the east, right here, and all the rest of the way across Wyoming, you don't have this thrust belt type of geometry. What you have is the basement rocks involved. So think of granite being caught up. Whereas to the west here, it is largely not. It's largely thin slices of sedimentary rocks. So you get a different type of mountains. You have these, so this is basement rock from 30,000 feet or so, shoved up on top of itself and on top of the sedimentary rocks. That's why you end up with these very deep basins. And this is the Grovant Range that is right here behind us, right behind me. That's what we see. So this sweeps all the way across the state of Wyoming. So if you drive to the Black Hills are another example of these basement chord uplifts with these deep basins in between. The Powder River Basin with all the coal in it is one of these basins. So if we look at this next slide, this is a cross-section through the town of Jackson from southwest to northeast. And again, you can see the thrust belt out here to the west. So think of the Snake River Range behind you out to the west. And you can see the basement rock, 25 or so thousand feet below the thrust belt. We look to the east here, though, and what we see is that basement rock is thrust up, shoved up very high in elevation. So you can see these rocks right here that are basically at the surface here, we can see them when we walk up Cache Creek, are 25 and more thousand feet below us, right here beneath our feet. There is a basin beneath the town of Jackson. It's actually part of the Green River Basin, which produces gas in a very prolific way at Pinedale Anticline and Jonah Fields. Those same rocks are beneath our feet, right here, between the Grovine Uplift and the thrust belt to the west of us here. So if somebody was really daring and was worried about having enough energy in the town of Jackson Hole, you know, it's possible. I don't think we'll ever see a rig in the middle of the town square, but it's possible that there's actually hydrocarbons in traps beneath the town of Jackson in this deep 25, almost 30,000 foot basin beneath us. So it is literally exactly the same rocks that produce just 80 miles to the southeast of us in the area of Pinedale Anticline. So, and this is the type of geometry, not this, but a deep basin and these mountain uplifts that we see again all the way from here, all the way across Wyoming, all the way to the Black Hills. So we come forward further in time to about 45, 55 million years ago. And that's about when the compressional event is ending here in Wyoming, at least. And there's something that's happening in this area, a major volcanic event that we speculate as to why it has occurred, and it may well have something to do with the end of that compressional event. There's a lot of argument about that. But there's volcanism, major volcanic sites just north of here. And you can see evidence on the geologic map of at least 3 or 4 just east of Yellowstone today. But this volcanism is not continuous over that 10 million year period. It's episodic. So in other words, think of the Cascades today. That's a very good example, analogy. The Cascades are a volcanic system, volcanoes. Mount St. Helens, Rainier, et cetera, are not erupting continuously. It's very episodically. It's pretty dramatic when they do happen. And that's what this diagram here on the left is attempting to show you, is that there's layer after layer after layer after layer. And in between the times of volcanism, think on the flanks of Mount Rainier, Mount St. Helens, you have these vast forests that develop across this landscape. And so there's evidence multiple times, many times over, of this whole northwestern part of Wyoming, in between these volcanic episodes, being covered in these vast forests. They're actually very similar to the redwood forest that we see out in northwestern United States today. So that's what happens for about 10 million years here in this area. But at the same time, just to the south of us, that volcanism is restricted to this area up here. You have something very different going on. You have the Green River Basin. So you have one of these intramontane basins between the Wind River mountain range and the thrust belt. You call it the Wyoming Range to the west. And this basin is sitting there, and sediments are being washed into it due to erosion over the course of millions of years. So you're filling that basin in. And there are lakes at different times in the bottom of that basin out there. And one of the most dramatic ones is Lake Goss or Fossil Lake. And how many of you have been down to Kemmer, been to Fossil Butte National Monument? Hopefully a few of you have. Okay, many of you have. I was going to say, if you haven't been there, it is a world-class fossil site. And the little museum there has some truly world-class fossils in it. You know, this time, 45, 55 million years ago, is often called the age of mammals. But if you look at what you can see is being recovered as fossils from that fossil lake, you can see it's also the time of reptiles, it's the time of fish, it's the time of amphibians and bats and birds and snakes and insects. In other words, there's a full spectrum, an incredible spectrum of incredibly well-preserved life that is seen from the fossils in these sediments down here just south of us. So for those of you who have not been there, I strongly encourage you to go down sometime, take a day trip, and visit that little museum down there. So let's start talking about more recent things. And to do that, to set the stage for that, I want to show you what the current plate tectonic setting is today. So we have the Pacific Ocean out to the west, North American plate here. North America is heading west about 1 inch a year. Pacific is heading to the northwest at about 3 inches a year. And remember those spreading centers in that ancestral Pacific Ocean. We see there's a little bit left here that hasn't been overridden by North America. That's the only place here on the North American craton continent where there is still compression going on, where there's still subduction going on, and that's why you have the Cascade volcanoes to the west. But that compressional event is very minor now with respect to North America, and we have extension going on instead. So let's see how that happened. So here we are 80 million years ago. So watch the red spreading centers, and then watch North America move to the west here as we go forward in time. So 80 million years ago, 60 million years ago, 40 million years ago, 20, and you're starting to override in a big way that spreading center, and then today. And you've basically overridden almost all of it. So it's 20 to 30 million years ago when you're really beginning to override that spreading center that you change from any compression at all to an extensional system across western North America. That extension that is the reason that Jackson Hole is here, the reason we have the dramatic Teton Range just to the northwest of us. And you can see this Basin and Range event all the way across the western US, all the way to the edge of the Sierra Nevada mountains. And that's what we see here within the yellow boundary on this image. That is the Basin and Range extension event that is underway today. And you can see that the Teton Range and Jackson Hole are within the edge of that boundary. So this is some of the most recent and ongoing extension that's occurring as a part of this ongoing extensional event that is affecting much of western North America. You can see that out to the east, it's undeformed. We still have these older, only 65 million years old, say, older compressional mountains that resulted from this compressional event. You can see, you can see the Black Hills out here, the Bighorn Mountains, the Wind Rivers, the Front Range, and so forth. And maybe the extensional event will migrate. It certainly is migrating to the east today. Otherwise, Jackson Hole wouldn't be here. How far it will extend, we do not know. But we can also, so that's why Jackson Hole is here now. It's because of this extensional event. The other thing, again, that we can see is the Snake River Plain, where Yellowstone started, say 16, 17 million years ago. It's migrated to where it is today. So we're going to talk about both of these things as well as glaciation in the rest of this talk here. So here is a diagram that I suspect most of you at least have seen before. We're talking about Yellowstone. Yellowstone, of course, is right here, just north of us. Here's Jackson Lake. Here's the Teton Range. Here's where Yellowstone began 16, 17 million years ago, and you can see other ancestral Yellowstones that existed and arrived at where Yellowstone is today. Now brown, and you can, those dates, those numbers on there are dates. Those are the rough ages of where those ancestral Yellowstones were as we go back 16, 17 million years in time. And you can see that they get younger as you get closer to Yellowstone today, as you would expect. Brown means the topography is fairly high. Green means the topography is fairly low. And what you see, of course, is that the Snake River Plain, for instance, is low, relatively speaking. We see the mountain ranges that wrap around the Snake River Plain. And actually, there's very good evidence. We know that these mountain ranges extended right through here before Yellowstone destroyed them. All right? The red dots in here of varying sizes represent seismicity. They represent earthquakes. So those are the location of earthquakes. And what you can see is a couple of things. I mean, of course, there's a heck of a lot of earthquakes around Yellowstone, but there are earthquakes that actually wrap all the way around in this brown, higher topography. This brown, higher topography is colder. So it's, relatively speaking, so it's brittle, and rocks form in cold rock like this by faults, by what we call earthquakes. If you look in the Snake River Plain there, you see that there are essentially no earthquakes at all. And the reason for that is because you have this hot Yellowstone system. It's still hot, I mean, basically all the way back here. Yellowstone is very hot, very near the surface, and that rock is too hot to deform brittly. So it deforms plastically. You don't get earthquakes. So if you're worried about earthquakes, you don't want to live in Jackson, you can go out and live out on the Snake River Plain, or other places, of course, as well. But one of the things I want to call your attention to here, and we'll come back to it at the very end, is the seismic gap. If you look in there, you'll see that there is almost no evidence of seismicity, of earthquakes occurring right here in Jackson Hole and along the Teton Fault. And that's something I want to come back to at the end, but I want to call your attention to it here now. So, what is Yellowstone? The short answer is we don't know. There are many competing theories, and there are people who will tell you vigorously and vehemently that it is this, or it is that, or it's not this, or it's not that. Here are just two models, in members, if you will. Certainly there are many people that believe that Yellowstone is a result of mantle plumes, hot rock that comes up all the way from the core mantle boundary, thousands of miles down. There are other people that think that's full of bunk, and that it is a result of relatively shallow processes in the upper mantle here. And it is a very complex story to unravel, because you have to, any explanation has to talk about the subducting plate to the west. You have to talk about the Newberry volcanic system, which is at Bend, which is basically a mirror image, if you will, of the Yellowstone system. It migrated from where Yellowstone began to where Newberry is today. There's a whole lot of things that make this far from a simple story, and all I want to leave you with is that there is hot rock there. We know that. We know that things are happening down there, and we're really just now beginning to get the data to maybe begin to unravel with any kind of definition what the answer is. So what we do know is that Yellowstone is one of the world's truly great volcanoes. And it's one of the few that is so big that's actually in the interior of a continent, like Yellowstone is. If you want to get a sense for how big the eruptions, some of the eruptions, a few of the eruptions have been from Yellowstone, you can look at, most of us in the room here, not quite everybody, but most of us are old enough to remember Mount St. Helens, 1980. Everybody, there were people that died, there was major devastation, and people thought, that's a big event. But if you went to try and find actually the layer of ash from that volcano, you would have a hard time finding it, even if you looked in this area here, and you probably could not find any evidence outside of that area there. In other words, there wasn't enough that was erupted and deposited to be able to find it much beyond that area in pink there. But if you go today to the Gulf Coast or to the Pacific Southwest of United States, you have a good chance, if you dig in the right places, of being able to find evidence, find an ash layer from the 640,000 year ago major eruptive event, the 1.3 million year ago one, and the 2.1 million year ago one in particular. So these are gigantic eruptions. And certainly all of North America would have had an ash layer over it. How big were they? This is a USGS diagram that gives some sense of that. And Mount St. Helens, so these circles, these blobs, are attempts to show the relative size in terms of cubic kilometers of material that was erupted from each of these volcanic events. Mount St. Helens is that one right there. I'll say about a half of a cubic kilometer of material was estimated to be erupted from Mount St. Helens. The biggest volcanic event in recorded human history is at Tambora in 1815, which is right here. And 1816 was often called the year without summer because of the impact on global climate of that eruptive event. It erupted an estimated about 50 cubic kilometers of material, as composed to a half of a cubic kilometer from Mount St. Helens. If you look back here at these eruptive events, and there's one additional one, Long Valley Caldera, which is out in California. If you look at these three from Yellowstone, here's the biggest one, 2.1 million years ago, and that is 2,500 estimated cubic kilometers of material. So if Tambora with 50 cubic kilometers caused, quote unquote, the year without summer following the eruptive event in 1815, we really don't know what the impact was, but it was clearly global and it clearly would have been very major, very dramatic. So these were major eruptive events. But is that typical of Yellowstone? The answer is no. Since that last major eruption about 640,000 years ago, there have been roughly 70 identified volcanic eruptions in Yellowstone. The last one was around 70,000 years ago. And any one of those would more than likely have been ones that if the Park Service weren't worried about the liability, as they are on Hawaii today, you could drive up nearby and look at the eruptive event. In other words, they were not these vast, cataclysmic types of eruptions that have occurred very occasionally. Most of the eruptions at Yellowstone are, relatively speaking, minor. Unless you had your house destroyed and from Kilauea here recently, though that was a minor eruption as well. But Yellowstone contains the world's greatest concentration of geothermal features. Something approaching half of the world's geothermal features are found in Yellowstone National Park. So it's not something that you can walk around and go elsewhere in the globe and see something that is comparable. Not on Kamchatka, not in New Zealand, not anywhere else on Earth. And it is because when you are in Yellowstone, you are literally within the confines of a volcano, that these incredible features that were the cause of the world's first national park. That's why it was created, and it's created because this is a volcano. So the extension is ongoing. We talked about that, and I said this is why Jackson Hole is here. And this is a diagram, a cross-section drawn through Jackson Hole, through the Grand Teton, and 2 points east and west. And what we see here is the Teton Fault circled by this red here. And the change in elevation from the top of the Grand Teton to the base down here, the displacement on that fault over the last 4 million years is something like around 25,000 feet, plus or minus a few thousand feet. So when you stand on the valley floor, say at the Bradley Taggart Lake parking lot, and look up at the Grand Teton, the rocks, when you look up Avalanche Canyon, you can see those carbonate rocks, up the canyon there. These ones that are shown as blue on the backside here, you can see them through the gaps, through the canyons. Those rocks that you can see up there at, say, 9 or 10,000 feet are perhaps 15, 18, 20,000 feet beneath your feet, down here in the bottom of this valley that we call Jackson Hole. There's a little bit of uplift, but most of the motion is down, is the valley flora dropping down. And there was, as I already said, and you may not have caught it before, the Gros Ventre Mountains went right through where the valley of Jackson Hole is before about 4 million years ago. So there was no Jackson Hole here, say 4 million years ago. There was a mountain range, there was the Gros Ventre that was formed by this compressional event about 65 or so million years ago. So you drop the top of part of the Gros Ventre range way down, and you lift that mountain range up a little bit, and the result of that then is this north-south oriented Jackson Hole and north-south oriented Teton range, which, if you remember that quasi-satellite image of the whole western U.S., that's what you see all the way from here to the Sierra Nevadas is you see those basins and ranges that are north-south oriented. And that's what we are in here, is the easternmost of one of these basin and range systems, and one of the youngest ones as well. And again, that's why, to a good extent, why the Teton Range is as dramatic as it is. And this is imagery taken off the internet. It's data that you can download, something called LIDAR, which basically, through algorithms, strips off all the vegetation and allows you to look in great detail at the land surface. So here's Bradley, here's Taggart Lake. This is a Google Earth image back here, and we've draped this on top of it. And what you can see here, this dark line is the trace of the Teton Fault right along the base of the Teton Mountain Range. So this is a real fault system. It's an active system. We'll come back to that. And you can see very clear evidence for it. And if anybody here has walked up Avalanche Canyon, just as a for instance, I know I've done it many times, and that's right here. You can see it's a beautiful glacially carved valley. But right here, if you have walked up Avalanche Canyon, you have scrambled up about a 20-foot high surface, pretty steep surface, that is the Teton Fault. And quite a few times, it wasn't until I saw this image I looked at it and said, damn, that's the Teton Fault. And I've climbed up it a whole bunch of times. In particular, you can see evidence of it in the offsets here on the lateral moraines. So all this material out here, these are basins carved by glaciers coming out of the Teton Range. And all this material that you're seeing out here and along the sides is glacial debris that we'll talk about more in a moment. So less than 15,000 years in age. And you can measure the amount of offset there in the last 15,000 years by looking at these offsets on the very clearly evident Teton Fault. So from a geological perspective, this is today. This is happening today, and it has been ongoing for the past 4 million years. So let's talk about glaciers then. We started on it right there. That was a good place to do it as well. Jackson Hole is one of the best places on Earth to see and talk about glacial features. Think of the Matterhorn. The Grand Teton is a horn, geologically speaking. This is as classic of a U-shaped valley, which is direct evidence of glaciation as you will ever see anywhere on Earth. You can see the basins that were carved out here, that was carved out by the glacier that came out of Cascade Canyon, causing Jenny Lake here, and the ring around it, the tree-covered ridge, is the terminal moraine, the end of where that glacier got to, and the debris that was pushed up by that glacier as it came out of Cascade Canyon, some 15,000 years ago. You can see more morainal material here with the trees on it. We'll talk about that in a second. You see a great big outwash channel here that comes from the Jackson Lake area down to past. There's past Jenny Lake. There's the Inner Park Road right there. And as we look to the north towards Jackson Lake, you can see this vast outwash channel that we call the Potholes area today. You notice there are no trees growing on it. You see all the trees on this, the burned ridge, and here up towards Signal Mountain. This is why Grand Teton National Park is here. I will argue vehemently, and it's because of this glacial system that existed here. What you see in Jackson Hole, and what you don't see if you go over the hill, just over here into Teton Valley, Idaho, is you did not have this glacial system operating like you did in Jackson Hole. You have this vast outwash plain from a glacier, we'll see in a moment, is thousands of feet thick and stretches from the Gros Ventre Mountains to the walls of the Tetons. So, in some places 15 and more miles across. A tremendous amount of water, and as it retreats and as it melts, there's tremendous outwash from all this material that the glacier is grinding up. But the glaciers, the material that the glaciers push together is incredibly unsorted. In other words, it has material from house-sized boulders to flower-sized material, and it's completely unsorted. The outwash here and here, what happens to all the fine materials? Where is all that fine material today? It's in the Pacific Ocean, or well on the way to the Pacific Ocean. So the fine material doesn't stay when you have this vast outwash of water. So the result of that is that where you do have the fine materials on the moraines, it holds water. And so it is an environment then that it holds enough water that you can grow trees. Out on this outwash plain, there's not a whole lot that grows out there beyond sagebrush and some grasses and things. So if you think about the people that came in here, 130 or so years ago and tried to farm, and if you go up and look at Mormon Row, they did an incredible amount of work, and they failed, basically. And they failed as a result of this, that they were trying to farm on a glacial outwash system where the water lands and it just goes straight down through. It doesn't linger near the surface. You don't have the fertile fields that you do over on the other side of the mountain right here. So I will argue that without this geologic feature like this geologic event, this valley would look like the valley does on the other side, and you can decide whether you think you like it this way or would like it like that. So if we go back about 14,000 years, this is a cartoon, if you will. It's a sketch of what the valley looked like. Teton Village is way down here at the bottom. You can see the valley glaciers, Jenny Lake here, Lee Lake. So these are the glaciers coming out of the canyons, smaller ones down here at Bradley and Taggart. And you can see this vast glacier that flowed out of Yellowstone, flowed out of the Toggetee Pass area. That's miles across, literally, and thousands of feet thick here. It's much more like a continental scale glacier than what we typically see in the Rocky Mountains, which are these alpine style of glaciers. So it has had a major impact on the landscape here, and it's had a major impact on the way we see and enjoy, I hope, this valley here today. If we look at a map of the extent, the maximum extent of the two most recent glacial events in Jackson Hole, again, these glaciers flowed south out of Yellowstone and out of the Toggetee Pass areas. We can see here's Jackson Lake up here. This is the extent, the maximum extent, about 15,000 years ago, the most recent, the Pinedale glacial event. It didn't get any further south than that. If you go back 130 roughly plus thousand years ago, the town of Jackson is right here. These red lines here mark the maximum extent of the Bull Lake glaciation that came all the way through here. Where we are today, there was roughly 1,500 feet of ice, 140, 150,000 years ago. And it extended all the way down, not quite to Hoback Junction, about where the last bridge goes over the Snake River at the south end of Hog Island is where the maximum glacial advance was. So there's Hoback Junction right there. So, and if you look right here, you see a line across here, and you probably can't read it, but it has a 9 on it. That 9 is representing 9,000 feet, which is the estimated elevation of the surface of the ice during that maximum Bull Lake glacial advance. That 9 sits almost right on top of Jackson Hole Airport. And for those of you who are not familiar with the elevation, Jackson Hole Airport sits right at about 6,400 feet. 6,400 from 9,000 is 2,600. There's a half mile of ice at that point, say 130, 150,000 years ago. So this valley was a very, very different place as you go back in time. I've tried to give you some sense of that, even that the valley wasn't here, say 4 million years ago. So, so this is a partial story. It's a highlights, best hits, if you will, a Cliff's Notes version of the geologic story of Jackson Hole and northwestern Wyoming. There's a whole lot more. You could talk for hours about many of these various topics. We're not going to. But what I want you to have a sense of is what that story is and just talk just for a moment about, and try and convince you if I haven't already, we haven't talked about all this, all of these things, our weather, our animal life, plant life, and certainly our human history, are a direct result. What we see today is a direct result of the geologic events that have happened here over the course of literally billions of years, and especially in the last 70 or so million years. If you think about weather, the Snake River Plain is the conduit for those big storm systems that come roaring up from the Pacific and drop the powder snow in the wintertime that people come here for. That mountain range that is oriented north-south is the reason why that snow, that precipitation drops right here, basically on Teton Village, on Targhee ski area. The type of rock is has a very direct impact on the type of flora that grow on those various rocks. The elevation has a big impact on both animal life and plant life. And again, we talked about, for instance, that glacial outwash plain. There's a very different environment there than what you see in the mountains and even on the moraines right next door there. And again, from a human history perspective, I will argue very strongly that we would not have a Grand Teton National Park here if we had an environment that looked like it is like it is on the other side of the hill over in Teton Valley, Idaho. And we're also fortunate, I will say, that we do not have a mineral belt that's, for instance, very similar to the one that stretches across central Colorado. People have looked for minerals here in Wyoming. They're relatively speaking, Wyoming is that kind of mineral poor, gold and silver and things like that. If there had been accumulations like that, they definitely would have been discovered in the Teton Range and all the other mountain ranges across Wyoming. And if you drive into central Colorado today, you see mountain towns, you see houses up on near old mine sites. In other words, there was a lot of fee land as a result of that mining, land that was not public land as a result of that mining. And if we had mineral riches like that, the Teton Range, I don't think would have been able to be protected as the park that it is today. So there would have been big chunks of private ground in there. So the geology really, I'm a geologist, and I look around and I see geology everywhere, but it is everywhere. And that's really one of the things I want to leave you with, is that there is not only a long geologic story here, not only are there an incredible number of things that contribute to this story, but that story contributes to what we see, why we're here. The world around us today is a direct result of that long geologic story. If you look out into the future, certainly earthquakes are going to continue to occur. You saw the seismicity around the Yellowstone system. We'll talk more about that in just a second. Yellowstone is one of the world's great volcanoes, the greatest concentration of geothermal features. Those will continue to bubble and burble and spray and everything else for the way out into the future. The more subtle things, ongoing erosion, helps shapes the valley, shapes the mountains, water flowing, ice and snow in the wintertime, is certainly part of the sculptor of the landscape that we know and we love. There are things that are more destructive and less common, these super volcanic eruptions, if you will, from Yellowstone, others that are more frequent, such as hydrothermal explosions, which occur fairly frequently up in Yellowstone and other things in between. And as a geologist, I can say we're not sure that we won't have glaciation again in North America in Jackson Hole. Speaking about geologic time, tens of thousands, hundreds of thousands, even millions of years, I certainly would not bet against more glacial events happening here in Jackson Hole. I'm not going to buy glacier insurance. I'm not worried about that. I don't have volcano insurance either. I do have earthquake insurance. So, if you want to sum it up in one slide, then this is the slide, the bullet points, if you will, of that almost 3 billion year geologic history. It does go back. There is evidence actually from some zircons of rocks actually 3 billion years or older here. You're talking about Precambrian intrusions, metamorphism. You're talking about the breakup of the supercontinent 750 million years ago, and we can see evidence of that in Mount Moraine. We're talking then about during the Paleozoic and the Mesozoic, for nearly 500 million years, Wyoming is near the equator. It drifts north with North America. You have deposition, periods of no deposition, periods of erosion, but Wyoming's flat and near sea level for nearly 500 million years. And then you have this major compressional event that starts, depending exactly where you're at and exactly what age you want to pick, 65, 70 million years ago. That sweeps all the way across the state of Wyoming, forming all the mountains and all the basins except the Absarokas and except for the Teton Range, all of it. And then you have these more recent, just in the last 60 or so million years, these dramatic events that formed the topography that we see today here. The major volcanism of the Absarokas, Yellowstone migrating to where it is today from where it was on the Oregon, Nevada, Idaho border 16, 17 million years ago. You end that compressional event, you begin this major extensional event that sweeps all the way from here to the Sierra Nevadas, and that is specifically and exactly what forms Jackson Hole, the valley that we live in here. And then you have these multiple major glacial events that started about 2.5 million years ago, and the most recent one ended only about 15,000 years ago. So, the geology controls all of this, and I make the point that it controls why we're here and why we see what we see, and why the parks, for instance, are here. So one last slide as I finish up, one last little bit about something on the Teton Fault. There is active, ongoing geologic research occurring in various places in Wyoming, and it certainly is here in Jackson Hole. And there is work that is being done on the Teton Fault system. And those of you who came to the talks that Darren Larson gave just back in August will have heard a little bit of this, some of this. He and some other researchers from other universities are looking at the Teton Fault system here, looking at the mountains, looking at the glacial systems, looking in the lakes. Darren in particular is looking at lake sediments. So the sediments in like Jenny Lake, the sediments in Lee Lake, Bradley, Taggart Lakes, Phelps Lake in particular. And so they are taking cores of these sediments and looking at them and seeing what they can see that would tell them about episodic seismicity. In other words, faults occurring, fault movement occurring on the Teton Fault system, earthquakes. And what they see is that they really do see evidence for these faults in the lake sediments. And what you see is the lake sediments themselves are very fine-grained, very, very fine-grained sediments. Think of it as mud, if you will. And what they see are these periodic pulses of slightly coarser material that is deposited episodically in amongst these finer sediments. And when you can correlate them from lake to lake, you have quite a bit of confidence that what you're seeing is the result of seismicity, earthquakes on the Teton Fault system. There was something really, really strange, though, about Darren's data set. And we were talking about that when he was here. And what they see, and this is all really new stuff, some of those cores were just acquired this past winter, here, late winter, early spring, is that there's evidence that for some reason, the seismicity appears to have stopped around 7,800 years ago. And that's really odd. I looked at that and I said, that can't be right. Darren, there's something wrong with your data set. But I went back and thought about it overnight, and there are some other data sets out there. And there's a lot of people doing a lot of different kinds of research here, and you need to put things together. And one of the data sets that is out there is one that the University of Utah and the USGS maintain both, they monitor seismicity, and they have very high resolution GPS stations on both sides of the Teton Fault and elsewhere. And what you see today is that there's clear evidence of compression across the Teton Fault today. And that really shouldn't be happening. I would be willing to bet that if you measured the dynamic system across every fault from here to the Sierra Nevadas, all these basin and range faults, every one would be under extension, being pulled apart. So what is the reason for that? Well, we don't know, but you know, the natural thing to think about and invoke is Yellowstone, which is a major uplift. It's above regional. It's a swelling, if you will, of a part of the continent here, and it's right next door. So my guess is, and I think Darren probably agrees with it, is that somehow or another the Yellowstone system for the last 7,800 years has locked the Teton Fault. We know that there is limited, almost no seismicity right now. It's probably a result of this compression across the Teton Fault. It's not pulling apart like an extensional fault should be. Obviously it has been for most of the last 4 million years, otherwise the valley wouldn't be here. So it's something very temporary in the geologic scale of things, but it's something that appears to be happening today. So you know, that's a real possibility. It's brand new data, brand new research. And you know, as I said it right up here, you know, there's always something new when we do research. You know, there's always something new and unexpected that can be, that often is, you know, often happens, you often find. So it is all about the geology, and go out and enjoy it. Yeah, I'll entertain a few questions for a little bit.
John, can you explain what causes the extension of faulting?
Well, what I'll try and make it real short and real simple, which is sort of hard. But North America and the Pacific Plate were heading at each other. The Pacific Plate was being subducted beneath North America, so they're headed at each other, and that causes compression. That Pacific Plate, the piece of it going back in time that was headed east, was coming from that spreading center. Once North America overrides that from the other direction, the other side of that spreading center, the oceanic plate was heading west-northwest. So you basically shut down that compressional event when North America overrides that spreading center that did exist out there, and a little piece of it still exists off of the coast of Oregon, Washington, and the Vancouver, BC area today. And that's why the Cascades are there.
So is it kind of like a spring that's being compressed, and now it's coming apart?
Well, there's a lot of good arguments about exactly how you do that. You know, you have compressed Western North America actually off and on for a couple 100 million years. It only reached into Wyoming as far east as about, you know, say 70, 65, 75 million years ago. So Western North America actually had been squeezed. You had all these, you know, rocks thrust on top of each other. There are competing arguments about exactly how the extension occurs. One is that you release that compression and you get sort of a collapse, if you will. There are a lot of things going on in the mantle underneath us, though, that are very complex that we don't understand very well yet. And so that, don't believe anything I just told you.
Are there any major compositional differences between the Grand and, say, Keweenaw or Nipissing, or is it purely a glacial coincidence that it's 1,000 feet higher?
Again, there's not necessarily an absolutely short answer to that either. There are differences in the rock, for sure. Major differences, though, probably have to do with the existence of features in the rock, faults, fractures. I don't know that I've seen where anybody has really done it in great detail, but I'd be willing to bet that the location of the major valleys that you see coming out of the Tetons are related to fracture systems, places where the rock was weaker. If you have a fracture in a rock and you start pouring water on it, where it's going to erode preferentially is where there's a weak spot, a break in the rock like that. So it's almost certainly a result of fractures in the rock and other changes in the rock composition. There are things you can see like the dikes that cause changes in composition. In some cases, like on Mount Moraine, it actually sticks out. It's more resistant to erosion than the rock around it there like that. There are other compositional, textural, and mineralogical differences, and those things actually are the evidence for this Himalayan style collisional event that we see from about 2.65 billion years ago. You have to look at the minerals, and there's a difference. You see differences as a result of the one continent riding over the other. Let's just let it go at that.
The fact that the granite is so much bigger is probably more a product of...
It's probably more a function of, well, it's a function of two things for sure. That's the point where you have maximum displacement on the Teton Fault, right in the middle of the fault system. And you probably had places to the north and the south that were just a little bit less resistant to erosion. Yes, sir, or ma'am.
You talked about the mountains and the moraines. What about the buttes? How were they formed?
First of all, I have to get on my geologic hobby horse and say there are no buttes in this valley. My wife will hit me later because it's one of my things. A butte has a very specific, as does a mesa, a very specific geologic definition. Has a flat top, a resistant layer. There is no such animal here. So East and West Grovant Butte. I don't know who named it, but they should be shot by every geologist. So your question again was, I got off my. How do they form? They represent. Remember that you had a mountain range that came through here before this extensional event. The Grovant Mountains, we say they end right over here today. They did go all the way through where the Tetons are into easternmost Idaho, and you can see evidence for that in the Tetons themselves. You can see faults and thrusts and things that are directly a result of that compressional event. So as you begin to stretch this area apart as a result of this extension, the Teton Fault, the valley floor drops. At the southern end of the Teton Fault, it gets a lot more complicated. You actually start to reuse the old laramide 65 million year old faults. And I'm not going to get into more detail than this and say that the fault system gets quite shallow here. And it's using the old fault system, and so it can't go as deep. That's part of the story, and so you end up with these relatively small rotated fault blocks, which you can see from the western edge of the Grovants through Miller Butte, through East Grovant Butte, West Grovant Butte, up Phillips Ridge, and over into Cold Creek Canyon is the westernmost of these faults that are associated with the Teton Fault system. So they're rotated fault, that's probably a lot more than you want. They're rotated fault blocks that are part of this basin and range extension.
So they are off cliffs.
They're dropping, the whole mountain range that was here is sort of gone. It's been dropped down. What we're seeing are rotated pieces of that pre-existing Grovant mountain range that went through here. That's another couple hour long discussion, if you will, and that's probably more complicated than it needed to be for you. But there's no real simple, easy answer other than they are clearly rotated fault blocks. There is, when you drive up to the fish hatchery, the highway there is on the trace of a fault. Small fault, But that face, it represents, it is basically, you're on a fault plane. And if you go west to West Grove Mountain Butte, Spring Gulch, thank you, is the next fault system back. And if you go over to the west side of Spring Gulch, and you walked along the east face of East Grove Mountain Butte, you're walking on the trace of a fault. Okay, so that thing is rotated like this, and you go back to the next one. So, I mean, those are rotated fault blocks. So they're very small, and that's what the Teton Range is in a much bigger scale, orders of magnitude bigger. It's dipping like this, and the valley floor has done this. It's a rotated fault block to some degree. That's why when you look on the backside, all the beds dip about 12 degrees to the west. It's been uplifted a little bit and rotated down on a fault system that's further west. Anything else I can't answer?
Blacktail Butte also part of that?
Oh, Blacktail Butte. You know, I thought for a long time that it probably was a rotated fault block. There's a very knowledgeable geologist that lives here by the name of Dave Adams. And his suggestion, and I'm more and more in favor of this interpretation the longer I look at this and think about it, it could well be a giant slide block. So as the valley floor dropped, and you start to form the face of the Tetons there, that's a very unstable situation. Things slide off of that. And it's quite possible, I've really warmed up to this interpretation, that Blacktail Butte is actually a large slide block that came off the face of the Tetons and slid out across and into the valley of what is today Jackson Hole. Relatively speaking, compared to a lot of other things we see around the world, that would be a very small slide block. So it's not at all inconceivable. But it's not, there are different interpretations, as there often are. Wes?
What surface would it have slid on?
Well, it would have fallen, if you will, failed off that face of that, that earlier, the Tetons. As the Tetons go up a little bit, and mostly the valley floor goes down. The valley floor is filling. There were lakes here, although that may or may not be important. It would have fallen, if you will, failed, come down, hit the valley floor. The valley floor would have been the surface it moved across.
We don't slide on either lake bed ancient lake bed surfaces or silt surfaces or fine grained surfaces.
Slope failures will slide. Gravity has its way. And if you have a steep slope, I could actually go back if you look at that LiDAR data set, you can see evidence of what would be smaller slope failures in a lot of places up and down the front of the Teton Range there. It's very common. This would be a much bigger one, but it's quite conceivable that that's what that is. There. Anything else I can't answer?
When we look at Yellowstone, it's higher than us. And then when we talk about the Snake River Plain as being the path of the hotspot, it's lower than us. Is that just because it eroded away, or the volcanics eroded?
No, it's because these were very violent, very large eruptive events, and you basically, simplistically speaking, blew apart the crust where this volcanic eruption occurred. So there were mountain ranges that went through where the Snake River Plain is today. The mountain ranges that you see to the north, the mountain ranges that you see to the south were continuous across the Snake River Plain. When you drive up into Yellowstone, the Absaroka Mountains actually extended further to the west. You can see what the Red Mountains down to the south, and you can see the Gallatin Range off to the northwest. There were mountain ranges there as well that have been destroyed by the more recent last couple of million years of last three major eruptions at Yellowstone. Yellowstone would be a deep caldera crater, except over the last 640,000 years, you've had volcanic eruptions, minor ones, relatively lava flows that have filled it in. So when you go up past what Lewis Lake Falls, you are going, that's about the point where you cross the boundary actually into the caldera. So once you get to Yellowstone Lake and you look around, you are well within the Yellowstone Caldera there. It's just been filled in over the last 500,000 years or so, like that. Snake River Plain is, Yellowstone is high because of a number of reasons. One, it's a very hot system. It's about 600 meters, 2,000 feet above regional as a result of all this hot rock over the course, a couple hundred miles wide that is underneath it there. So the craton, the crust is uplifted. If Yellowstone moves on, or if it cools and doesn't erupt further, we don't know, that area will subside, and that's what you see in the wake behind it that the Snake River Plain is. It is the wake, in a way, of that old Yellowstone system. So you have destroyed, literally, the mountains that did go across there as a result of these major volcanic eruptions. Literally.
Roughly how old is the Snake River, given it cuts through a number of the mountains, et cetera? When did it start to form as we know today?
The Snake River Plain?
The Snake River itself.
Oh. Let's just, the Snake River that we know today, there would have been a track down that Snake River Plain moving to the east as a result of those major volcanic eruptions. So very simplistically, I guess I'll say it started, not long after Yellowstone did and started moving east 15, 16 million years ago. It's a lot more complex than that, I'm afraid, because there are a lot of stories about regional uplift and tilts and whatnot of the western U.S. as a result of things that we're not all that certain about how they have happened.